Welcome to this introductory video from my series about probability theory. Here I cover all important concepts, starting right at the fundamentals. Let's start with the content of this first chapter, in which we define probability. For this, we need sample spaces to describe the outcomes of random experiments. Then we will use set theory to manipulate these descriptions using the famous De Morgan's rules. Finally, everything is combined in the naive definition of probability, which forms the basis for everything that will come after it. Let's start with our sample spaces. In probability theory, everything revolves around the description of random experiments. The outcome of an experiment has a certain probability and is unknown until the experiment is actually performed. Sample spaces contain all possible outcomes of an experiment. They can be finite or infinite, but it is easier to draw a limited sample space, so we will start with that. In this case, we have 9 possible outcomes of an experiment. Performing the experiment is like throwing a dart arrow onto the sample space. We call this sampling. It is also possible to define subsets, so parts of the full sample space. These are called events, and we say that an event A occurred if the outcome of the experiment is in A. Notice that the sample space is partitioned into equally sized samples. Again, thinking about the darts analogy, this would mean that all the outcomes of the experiment are equally likely. Of course, this is a special case which we will extend later on. As we have seen, the possible outcomes of an experiment can be collected into a set. Thus, set theory is a very natural way of handling and describing events and sample spaces. Let's again take a look at our sample space of 9 possible outcomes. We define 2 events, A and B. By using set operators, we can create new sets, such as the union of A and B. Another set operator we could use is the intersection. For a single set, it is possible to obtain everything that is not covered by the set itself using the complement. Here, the complement of A contains everything of our sample space that is not in A. When dealing with probabilities, it is often useful to think about expressing an event in more than just one way. Maybe it is possible to find an expression in which it is easier to deal with the event compared to the original description. De Morgan's laws can often help to reformulate the combination of sets. In the first law, we have the complement of the union of 2 sets. This is equal to the intersection of the individual complements. The second law states that the complement of the intersection is the same as the union of the individual complements. You can remember these laws by moving the complement into the brackets and then changing the set operator. A union becomes the intersection, while the intersection becomes the union. We will now illustrate how these 2 laws work at the example of our sample space. Again, we have events A and B. In the first De Morgan's law, we obtain the following subset of the sample space. The complement of A is everything not covered by A, and the complement of B is everything not covered by B. Now we perform the intersection of these 2 sets, which is everything of the sample space where both complements exist. Thus, the left and the right side of the De Morgan's laws are the same. We can do the same for the second De Morgan's law. In this case, we obtain the complement of the intersection of the 2 sets. The intersection would be the lower left corner of the sample space. Thus, the complement is everything except this one sample. On the right-hand side, we have the complement of A and the complement of B. The union of these 2 is again the same subset of the sample space as obtained by the left-hand side of the De Morgan's law. We will now move on to a more concrete example using actual probabilities. In this case, a coin flip is observed 3 times, which is our experiment. The possible outcomes of this experiment are all the different combinations of heads and tails of the 3 coin tosses, so 8 samples. This becomes our sample space. Let's take a look at some events. Consider the event that the first result is heads. We can count the number of samples that fulfill this condition. This becomes our event 1. 4 out of 8 samples satisfy this condition, so the probability of the event that the first result is heads is 1/2. The second event occurs when at least one result of the coin tosses is tails. Let's again count the cases in which this is fulfilled. We get 7 out of the 8 samples, so a probability of 7/8. In the third example event, we take a look at the event where all coin tosses result in heads. This is only true in 1 of the 8 cases, so we have a probability of 1/8. Think back to the set operators. We could apply our knowledge here and for example say that event A1 is the complement of A2. We will see how to write this down mathematically in the next part, when we introduce the concept of naive probability. Naive probabilities are simply defined by counting, exactly as we have done it before. We count the numbers of ways an event can happen and divide it by the number of samples in the sample space. Such a definition is very restrictive and is thus called the naive definition of probability. However, in the next parts of the video series, we will also cover other definitions. Let's again take a look at an example sample space with an event A. A consists of 4 samples and the sample space is of size 6, so the probability of A is 2/3. We can also introduce the complement of A again and see that the probability of it is 1/3. In general, it is possible to compute the probability of an event using 1 minus the probability of its complement. This holds, since by definition the set A and its complement together describe the full possible outcome space of the random experiment. Of course, the probability that any outcome occurs is 1. I hope this video helped you in understanding the basics for all of probability theory. If you want to continue on this journey, click here to find the next parts of this video series.